In this video, we are going to demonstrate the use of the Link Commander module. The Link Commander performs link analysis of an antenna measurement system, a data communication system, or can also be used to determine simple signal-to-noise ratio. Additional figures such as the receive power and bit rates can also be calculated. To begin with, we're first going to generate a dipole and transfer the dipole data into the Link Commander. Once we've opened the antenna simulation library, we're going to select the appropriate antenna from the list of standard references. In this case, we want to select an ideal quarter wave dipole. We're going to analyze it as a Wi-Fi dipole from 2 to 3 GHz with 101 frequency points. We're also going to horizontally position the dipole. Now we're just going to generate a simple azimuth sweep, and then we're going to transfer that data into register 1. To invoke the Link Commander, we click the Link Commander button. The Link Commander simulations begin from the signal generator. The defaults for power and frequency settings can be set manually. By default, they are set to 1 GHz to 20 GHz and 0 dBm to 50 dBm. As the sliders are changed, the power is changed along the cables in absolute watts. The signal generator passes through the link attenuator gain offset, which we will demonstrate when we calculate the maximum range. When going into the transfer antenna, which is our reference, we have access to any one of our 4 registers. Remember, we stored our dipole data in register 1. We also have standard reference data should you choose to enter a constant gain figure. We may also use the DAMS reference antenna, assuming it has been imported. When we recall a register, the as-L pointing angle becomes modifiable, enabling the user to specify a specific pointing angle. The transmit antenna follows through the path loss, which also has similar attributes as shown here. For example, the distance and the unit of measurement can be set manually. In this case, it's set to 120 inches. You can change the units of measurements to feet, meters, miles, and so on. It can also be calculated if the reference button is pressed. Any selected reference button sets that parameter for calculation while the other parameter is a constant. The default is to calculate the entire data link, hence the link reference button being shown as active here. If we are interested in temperature effect, then we can set the temperature. In this case, I'm going to set it to just under 23 degrees centigrade. Next, I'm going to specify a receiver antenna where simple constants can be entered. When a register is recalled, the signal generator is set to the register's associated measurement frequency, while power is still an independent variable. As signal comes through the receive antenna, we have the option of including an LNA with noise and gain. We have a built-in filter, and the bandwidth of the filter can also be set manually. The default is 10 MHz to 1 GHz. This can be adjusted in frequency, which we can see on the spectrum analyzer. When we see this on the spectrum analyzer, the noise dip is produced by the filter. When the filter is aligned with the signal-to-noise ratio increases. The link power is also displayed. We will now recall the dipole data we've generated. When we do this, the reference data is no longer modifiable, but the pointing angle of the dipole is. At 0, 0, the dipole has exhibited maximum gain. We're now at 120 inches at about 23 degrees centigrade, and we have a reference value of 2 dB on the receive end. When I recall the data of the same dipole on the receiving antenna, we can see the pointing angle is once again modifiable. As I move towards the filter, I'm going to adjust it down to about 30 MHz, and I'm going to position the filter at 2.4 GHz, which is the standard Wi-Fi frequency. I'm also going to adjust the frequency down to 2.4 GHz on the signal generator. Also on the signal generator, we'll notice that the frequency min-max is no longer modifiable. We're now set at 0 dBm and we have a signal-to-noise ratio of 53 dB, showing the link is stable. What we're going to do now is to determine the 10 dB signal-to-noise ratio distance. To do this, we click the path loss reference button, changing it to a calculated item. At this point, the independent attenuator can be increased with the calculation in the path loss, which maintains the dependent variables. As the attenuator is increased, the signal-to-noise ratio drops down. So now we're going to reduce the attenuation until we find our desired 10 dB signal-to-noise ratio. The assumption is that the modulation requires a minimum of 10 dB signal-to-noise ratio. The path loss calculation now shows 19,000 inches. Or, if we convert this to feet, that's 1,500 feet. So, in conclusion, we've established our transmit power was 0 dB, 1 milliwatt, our attenuation was 44 dB, our dipole gain was 2.1 dB, and our calculated associated path loss for a 10 dB signal-to-noise ratio is 1,500 feet. If I'm also interested in the associated bit rate with this 30 MHz filter bandwidth, then I can invoke the bit rate plot. The sampling occurs as the generator sweeps and the spectrum analyzer displays this. We can see what is beginning to emerge at 2.4 GHz is a bit rate of about 90 megabits. Realistically, however, this is also based on Shannon's limit, so it's not easy to achieve. Any other item that can be calculated can be done by pressing its associated reference button. If one were to determine the necessary receive gain for known transmit paths, signal-to-noise ratio, and generator power, then we would just deselect the reference button on the receive antenna until that signal-to-noise ratio came in using the path attenuator offset. While our system universally calculates any one of the 4 parameters, there are also a number of other special functions which can be accomplished with the Link Commander. And this concludes our video tutorial on the Link Commander module for the DAMS Antenna Studio. We hope it was informative and helpful. Thanks for watching.